Hello, welcome to class, April the 24th. I know a lot of you had your pre-cal test. Hopefully that went well. Hopefully if it didn't go well, you're not too sad right before the weekend. Um, but yeah, so today we're going to keep going through circuits. We'll finish up our classwork. I do have a warm-up that I want you to do. You'll write out the warm-up and you'll turn it in for a homework grade. So we'll start with that first, just a little bit additional practice about simple series and parallel circuits before next week we get into more complicated circuits. So we'll finish up the classwork, you have the warm up, and then you're also going to finish the homework in order to get those finished. All right, so we start off. We have a 6-volt battery, a 10 ohm, and a 15 ohm light bulb. We have wires with negligible resistance, so pretty much like all the wires, we're assuming these things don't have any resistance. So the first one, we want to connect the circuit with the light bulbs in series. All right, so series means I want to go one after the other. So let's draw this circuit nice and big so I can write all over it. So we have a 6-volt battery. Send this out. It goes through one resistor, and then it goes through the other resistor. It doesn't matter what order we put in. We just have a 10 ohm resistor and a 15 ohm resistor. So series only has one path through the circuit. So we want to find the total current, resistance, and power for the circuit. So the first thing we should probably start with is just total resistance. So total resistance in series, we just add these up. So resistance 1 plus resistance 2, or 10 plus 15 ohms. So that's pretty easy. Our total resistance is just 25 ohms. And back to our analogy of a grocery store, right? So here we're at a grocery store. In series, I have to go through the first checkout line and the second checkout line. So because I have to go through this one and this one, I end up with a big resistance. So in series, my total resistance is going to be bigger than my biggest individual resistance. So in series, we always get really big resistances because we have to go through all of the resistors, one after the other. So now we have resistance. We can get our current. I have my total voltage. I have my total resistance. So total voltage equals total current times total resistance, Ohm's law. Current, I just divide resistance over. So total current is going to be total voltage divided by total resistance. So I have a 6-volt battery, 25 ohms resistance for this whole thing. So if I divide by 25, I could just multiply the top by 4 and then divide by 100. So that'd be 24 divided by 100. So you should get 0.24, right? Something like that. 6 divided by 25, 0.24 amps. All right. And so that's the other thing. So current is like how many people are leaving this store. So if I have to go through this line and this line, we have a high resistance, so we're going to expect a lower current. No, we don't have anything to compare this to yet. We'll see that when we do part 2. But yeah, I expect a high resistance in series because I have to go through all of the checkout lines. So a small number of people are getting through a small amount of current. And then we can find our total power. So power is just current times voltage. So we have a current of 0.24 amps times 6 volts for our battery. 4 times 6 should be 1.44 watts. Yeah, Yeah, so 1.44. Oh, okay. Yeah, I actually don't know what happened to get one. All right, so those are our totals. I can get my entire circuit values, but I could also get my individual values for each resistor. So let's start off with my smaller resistor. Let's start off trying to find the values for the 10 ohm resistor. So starting off, I want to find current, resistance, and power for each resistor. So starting off with current, so again, back to our definitions, current is the amount of charge moving through our circuit, and that's back to the equation that current is equal to the charge going through the circuit per time. So how much charge moves past the point per time. Charge is made up of electrons. So electrons aren't being created or destroyed. We need a really, really high energy event to create or destroy electrons. That's not happening with a 6-volt battery. Yeah, we're talking about like thousands or millions of volts or even billions or trillions of volts type of things in order to really create or destroy electrons. So we're not doing that. We have so many electrons go out, all those electrons have to return. So when this goes out, I have 0.24 amps going through. So I have 0.24 coulombs of charge per second passing through this point. All of that charge has to go through here. The charge isn't getting created or destroyed. All of that charge has to go through here. Electrons not being created or destroyed. So all of that charge is returning to the battery. So we don't have enough energy to be destroying or creating electrons. Heptavolts. I mean, yeah, it really is ridiculous amounts of energy. So like large atomic bombs, again, small amounts of electrons can be created or destroyed, but still not a lot. We're talking to consistently create or destroy electrons, particle accelerators, or like supernovas, like large stellar events. Not even the sun does it at a very high rate, but yeah, it does happen within the sun, just not at a consistent rate. So we're talking just ridiculous amounts of energy to create or destroy electrons. So that means the current through this 10 ohm resistor is going to be all 0.24 amps. And we can also jump all the way down to our 15 ohm resistor. It's going to look identical. The 15 ohm resistor we're going to see is also going to get all 0.24 amps. So that leads us back to our rules. So remember, we had 4 rules that were important. So in series, each resistor gets the full current. That was our first rule. It has V-line? What? All right. I don't know why I said resistance for each light bulb. I already gave that. So I think I just copied and pasted. So we don't need to find the resistance. We already know the resistance. But we do need to find the voltage. That's what I should have said. So I can get the voltage drop for each resistor. So the voltage drop is going to be, that 10 ohm resistor is going to be the current of through the 10 ohm resistor times that resistance of the 10 ohm resistor. So the voltage drop is going to be current is 0.24 amps times resistance is 10 ohms. 0.24 times 10 is 2.4. So the voltage drop across that 10 ohm resistor is 2.4 volts. And this is just the magnitude. Obviously, it's a voltage drop, so it goes down by that amount. We can get the voltage drop across the 15 ohm resistor. Current is also 0.24 amps. This has a 15 ohm resistance. 2.4 plus 1.2 is 3.6. It's going to be the magnitude of voltage drop. Let's write that over here. So the magnitude of voltage drop across the 15 ohm resistor is going to be 3.6 volts. And so we can look at that here. I go out of my 6-volt battery. I end up going through here. I add 6 volts to my circuit. So I have 6 volts right here. I go across this 10 ohm resistor. The 10 ohm resistor, I lose 2.4 volts. So by the time I get over here, 6 minus 2.4, I have 3.6 volts here. 3.6 volts, well, across this resistor, I lose 3.6 volts. So when I lose 3.6 volts, I end up going down to 0 volts. So I send 6 volts to the battery. This resistor takes up 2.4 of the volts. This takes up the remaining 3.6 of the volts. So I end up going back down to 0. So we see here that each resistor is not getting the entire 6 volts. We see here the resistors are splitting up that total voltage. So that's the other rule, is that resistors split up and share the voltage. And the two ways of writing this for series would be that the voltage drop for resistor 1 equals the voltage drop for resistor 2 equals the voltage supplied by the, what am I saying, plus. So if I add these up, let's rewrite that. So the voltage drop for resistor 1 plus the voltage drop for resistor 2 is equal to the voltage provided by the battery. But these all get the full current. So I could also say the current through resistor 1 equals the current through resistor 2 equals that total current. So they all get that full current, but they have to share the voltage. All right, then I can solve for the power of each resistor. So power is just current times voltage. So power for this 10 ohm resistor is current through the 10 ohm resistor times voltage drop across the 10 ohm resistor, so it gets 0.24 amps. This one has a voltage drop of 2.4 volts. What was 24 squared again? What is that, like 580? 2.4 times 0.24, 576. Yeah, off by just a little bit. So the power for this 10 ohm resistor is 0.576 watts. Then I can get the power across the used by the 15 ohm resistor is that 0.24 amps. This has a voltage drop of 3.6 volts. Six times 0.24. This is a 0.864 watts used up. So the 15 ohm resistor here is taking up more of the power. Again, power is related to brightness. So we would see that this 0.864 watt light bulb is brighter than this light bulb. So power is what we're using to determine brightness. So in series, we see the bigger resistor, the light bulb with more resistance, is taking more of that power, which means it's going to be brighter than the lower one. And I can also add these up. 0.576 plus 0.864 is going to give us exactly 1.44. And this isn't going to be a rule that's different. This is always I can add up the powers to get my total power, right? This is just like energy. Energy is a scalar. I can always just add up the power of each light bulb, and that will add up to my total power here. All right, so which one of these is brighter? Obviously, this one is brighter, so the 15 ohm resistor is brighter. 15 ohm bulb is brighter. Let's see, because it has more power. And then if one of these light bulbs burns out, what happens? So I only have one path for current to flow, so that's like in there. So again, kind of hard to see, but in series, because they're having to share voltage, we end up with smaller powers, and so they're not very lit up. We can see maybe this one is barely lit up, and you can see this one is also barely lit up. But when one of these burns out, that path is no longer there. So that light bulb burns out, it's like it's no longer there. So this light bulb just completely goes away. Yeah, theoretically, which one would burn out faster? I mean, it really depends. If they're equivalent, what ends up burning these out? These are incandescent. What they do is they send a current across, and that heats up the filament. So it really depends on how the filament is made. I can't really say this. Yeah, it depends way too much on manufacturing and how it's made and what it's made of. So yeah, I take that back. I can't really make a statement on that one. But yeah, if one of these burns out, then the other one completely turns off. It turns into an open circuit, and both lose power. So if one light bulb burns out, we get an open circuit. Therefore, the other bulb turns off. Or the other way of putting that is just no current. So if it doesn't get any current, there's no electricity flowing through it, so it just completely turns off. All right, so that's our series. We'll come back to this for question 3, but now we're going to put these in parallel. Again, I'm going to draw this out rather large. It might be good for you to do that also. I'm actually going to try to draw this even bigger than the last one. So I have a 6-volt battery. Parallel, I have individual paths for each resistor. So it doesn't matter which one we put where. I'll put my 10 ohm resistor here and my 15 ohm resistor here. All right, now parallel. This is like a normal circuit. Breaking an incandescent light bulb? No, it's just tungsten. There's nothing in there. There's argon gas inside, but the atmosphere is 1% argon. Yeah, you're not gonna. There's nothing bad about this. You don't want to break the newer light bulbs. The CFL light bulbs, those you don't want to break because they have mercury in them a lot of times. Unless they're really yellow, then it might be sodium. But yeah, don't break the little spiral looking ones. The LED ones, it doesn't matter so much if it breaks. I mean, other than obviously it's glass. So the little spiral looking ones, don't break those and like breathe in the fumes. That's mercury, and mercury is not good for you. All right, so this is a parallel circuit. So parallel circuit, this is like a normal grocery store where I could go through this one or this line. So because I have a choice, I only have to go through one of these. It's going to be easier to get through the circuit. So this one is one where we're expecting a lot lower resistances. I expect my resistance to be smaller than the smallest resistance. So series, my resistance was bigger than my biggest resistance, than my biggest individual resistor. Here, I expect my total resistance to be smaller than my smallest resistor. So we're going to get a total resistance less than 10. So when we get our total resistance in series, it's 1 over the total resistance equals 1 over resistance 1 plus 1 over resistance 2. So 1 over total resistance is equal to 1 over 10 ohms plus 1 over 15 ohms. But this is 1 over resistance, so to get rid of that fraction, I do to the negative 1. So let's see this. So I need to invert all of that afterwards. So 1 divided by 10 plus 1 divided by 15 inverted. And we end up with 6. It's almost like I chose this for a reason. All right, so our total resistance ends up being 6 ohms. I actually don't think I chose that to be exactly 10 ohms, but I did choose it to where like 1/10 and 1/15 added together nicely. All right, so we see here again, because I can go through here or here, it's easier to get through. So I have a small resistance. So my resistance is smaller than my 10 ohm resistor. So total resistance for series was 25 ohms, bigger than 15 ohms. But in parallel, my total resistance is smaller than my smallest at 10 ohms. So small resistance means I'm going to get a bigger current. Last time was 0.24 amps. I expect a much bigger current than that. So total voltage equals total current times total resistance, or total current equals total voltage divided by resistance, right? Divide resistance over. Well, I have 6 volts provided and 6 ohms resistance. So my total current is 1 full amp. So we get about 4 times the current. Again, makes sense. If I can go through here or here, more people are able to leave the store than if I made everyone go through both lines. And it was hard to get people through and less people were leaving the store per second. All right. Then I also want to get my total power. So total power is total current times total resistance. So I have 1 amp, not resistance, voltage. Sorry, power is current times voltage. 1 amp, 6 volts. So I have 6 watts of total power. It's my other thing. I have a bigger power output, which can be kind of seen with the brightness, right? Again, brightness and power are related. So when I put these in series, they were really dim. You can barely see these lighting up, right? Yeah, you can barely see this one lighting up. This one does light up. You just can't see it very well. They are supposed to be identical light bulbs, but there's obviously manufacturing differences. So we have this one here, and we can put this here. So if I put this in parallel, they each have a full path through the battery. Get in there. Wires are getting kind of bent. There you go. We'll get this one in here. So we notice these are a lot brighter, right? When we connect both of these, are a lot brighter than the other ones. And so that's an obvious way of saying, hey, this is a lot more power. These are brighter, there's more power. So 6 watts of power versus just 1.44 watts of power. So putting these in parallel gives us a lot more. The hardest math ever. Yeah, 1 times anything is so hard. All right. So we have this. Now we want to find the current, voltage, and resist and power for each light bulb. So we have our 10 ohm light bulb to look at, and we have our 15 ohm light bulb to look at. All right, so starting off, let's start off with our voltage. Again, voltage only drops if I go across a resistor. So going up here, I haven't gotten to a resistor yet. So I have all 6 volts from the battery. No resistors, all 6 volts of the battery. In the real world, it's slightly off because our wires have resistance, but not too bad. So no resistance, don't lose voltage. But by the time I get back to my battery, I'm going to have no voltage. And so when I have this, it's pretty much like this is directly connected to the battery, and this one is directly connected to the battery. So both of these are getting that full 6 volts. So the voltage drop across that 10 ohm resistor is the entire 6 volts from the battery. And the voltage drop across the 15 ohm resistor is also that entire 6 volts. So this is the difference between series and parallel. So in a parallel circuit, each resistor gets the full voltage, the full circuit voltage. Or the way of writing that would be our total voltage is equal to the voltage drop across that first resistor is equal to the voltage drop across the second resistor. So they don't have to share the voltage. They each get that entire voltage. Now we get to the thing they do have to share. They do have to share current, right? Current is the electrical charge moving through the circuit. So I send a total current up this way, but current is those moving electrons. So I have 1 amp of current going through here, but now that charge has to make a choice. The electrons aren't going to go through both paths simultaneously, again, ignoring quantum mechanics, but they make a choice. So some of my current has to go this way, and some of my current has to go this way. So they have to split up. So I have current through my 15 ohm resistor going this way, current through the 10 ohm resistor going that way. So they're going to have to share these currents. But then it gets here, we didn't create or destroy any of the electrons. And so the electrons combine back together. So once these rejoin, I'm back to my full number of electrons. So I go back to having an entire 1 amp of current right here. So let's actually solve for this. We can get current, again, using Ohm's law. So current is going to be, well, I should probably write that from the beginning. So voltage equals current times resistance. So current is going to be voltage divided by resistance. We're looking at our 10 ohm resistor here. So the voltage drop, these each get the full 6 volts. The 10 ohm resistor has a resistance of 10 ohms. Crazy, I know. 6 divided by 10, we get a current across that 10 ohm resistor is 0.6 amps. So now we see this has a smaller resistance than this one, so more current wants to go through here. This is the better person at checking out. The less resistance, more people want to go through the checkout line with less resistance. So this takes up 0.6 of the entirety of the 1 amp. So this is taking up the majority of the current. And we're going to see here the current through the 15 ohm resistor is going to be the voltage drop is 6 volts divided by 15 ohms. 6 divided by 15 is the same as 12 divided by 30, which, man, I'm going to calculate. It's going to be 0.4. 0.4 amps. So current through the 15 ohm resistor is 0.4 amps. And so this is a bigger resistor, so it takes slightly less of that current. So we see here, each resistor got the full circuit voltage in parallel, but in parallel, the resistors share that current. Resistors split up the current. And so we see we're going to have the equation, our total current is going to be that current through path 1 plus the current through path 2. So 0.6 amps go this way, and no, that was 0.4 amps went this way, sorry. 0.4 amps went this way, and 0.6 amps went this way. So the 1 amp split up. Some charge went this way, some charge went this way. Some customers go to this line, some customers go to that line. More customers go through the line with a smaller resistance of checking out than with a bigger resistance of checking out. But once I get here, they all end up leaving the store. 0.6 plus 0.4 equals 1, so all 1 amp goes through here. All right? And by the way, these are called Kirchhoff's laws. The things I'm talking about, I'm just pretty much doing what's called Kirchhoff's law and everything but name. All right, so we have current. Now we can get our power. So power is current times voltage. So we're looking at our 10 ohm resistor here. The 10 ohm resistor got 0.6 amps. Both of these get the entire 6 volts from the battery. 6 times 6 is 36 divided by 10 is 3.6. Power through the 10 ohm resistor is 3.6 watts. Power for the 15 ohm resistor, this only gets 0.4 amps, but it gets the full 6 volts. 4 times 6 is 24, divided by 10 is 2.4. So the power for the 15 ohm resistor is 2.4 watts. And we see, just like always, 3.6 plus 2.4 equals 6 watts. So a thing that's always true is just going to be that total power equals the power through resistor 1 plus the power through resistor 2. So this is always true. Doesn't matter if we're series or parallel, I can add up the powers to get total power. All right? So answering the other question, so which bulb is the brightest? Well, more power means brighter. So this one is brighter because it has more power. So we see kind of a switch here. In the series, the one with more resistance took more of the power, but here the one with less resistance took more power. So it's a little bit backwards here. And then asking if one of the light bulb burns out, what happens to the other one? So again, let's turn our light off. There we go. So they're both on. If I disconnect one of these, so I disconnected that one, this one turns off, but this still has a full path. The battery goes here, through here, and then back to the battery. So if one of these turns off, there's still a complete path back to the other one. If I had this one on and I unscrew this one, that one still has a complete path back to the battery. So if I disconnect a light bulb, both of them stay lit. So if I disconnect a light bulb, running out of space, right? D right here. Both the other light bulb stays on. And then even more kind of interesting thing that happens, power, remember we also had power as voltage squared divided by resistance. So let's say if I'm looking at just say resistor 1, if I unplug this, well, they each got the 6 volts, so I didn't change the voltage. I didn't change the resistance. So not only does the other bulb stays on, it also stays on with the same brightness. And so we can look at this even one more time. What are you doing? Oh, you have to actually be plugged in, obviously. So they're really bright. So notice they're pretty bright. Whenever I unscrew this one, the brightness of that one doesn't change whatsoever. So I'm not changing the power at all for the other light bulb when I unscrew this. That's a really nice thing about parallel. I can plug something in and everything keeps drawing the same amount of power. And this is one of the benefits for having your house in parallel. We do have a disadvantage though. Again, if I keep plugging things in, as I add more checkout lines in a store, resistance goes down, it's easier to leave. When resistance goes down, current goes up. When current goes up, power goes up. When power goes up, we have a lot more energy being lost to heat. So things start getting hot. You can start catching fire to things. So yeah. So the power and voltage from parallel to series switch, you see they do a lot of switching, which one gets more, which one gets less, things like that. And then finally, the last little bit is 3. I know this warm-up is taking a long time, but the rest of the classwork shouldn't take too long. So that should be okay. So 3, which battery will die first? So when we're looking at it, when a battery dies, what does that battery run out of? Life force, not life force. So 3. So dead battery runs out of energy. So we're asking which one runs out of energy. First. Well, the only thing we're talking about that has energy in it is power is the amount of energy used per time. So these all have the same amount of energy, right? I connected them to the same battery. So for 1 and 2, they're both connected to the same 6-volt battery. So I'm not changing the amount of energy that's in the battery. But what I am changing is the power. So if I have a big power, that means the amount of time has to go down. Or an easier way would be if I multiply time over power times time equals energy. So if it has a constant amount of energy, if I have a big power, I have a small amount of time this will last for, right? Power is the rate I use energy. If I have a high power, I'm using energy very quickly. So whichever one has more power dies first. That means the parallel battery dies first. And we can kind of see that with our light bulbs, right? When I put these in series, the light bulbs are really dim, so it's not using much of the energy. But when I put these in parallel, they were really bright, so it's using up energy at a faster rate. No ritual things are happening with the batteries. But yeah, so that's a lot of advantages with parallel, but yeah, that is one of the disadvantages is you are going to run out of energy in the battery first. All right, so finish those. Again, there's a whole lot going here, right? That simple question, how much I can ask about this. So I filled up pretty much 2 full pages with this. This is going to be what most of your test is going to be. I'm not going to ask every single one of these, but I can ask any individual part of this. All right, so try not to waste more time, make this video as short as I can. The last one was a little bit long. Last little bit, we're gonna finish up our classwork. So we did the parts with the circuits. Again, I try to make the classwork as similar as much as possible to the homework. If you can't get to the classwork, try just refreshing the page. Sometimes Classroom freaks out. Oh, there's a cat sleeping. Well, here's the classwork. So we're on number 4. We'll do number 4 through the end. 4, we're given 3 identical light bulbs and a battery with plenty of wires with no resistance. So A wants us to draw a circuit where each light bulb receives current, so I can't draw this with a light bulb just not connected to the battery. But the resistance will be the greatest. So if I want a lot of resistance, I want the current to have to go through all of the resistors, right? So to get a lot of resistance, I want this to be like the store where you have to go through every single checkout line. So I want this to go through 1, 2, 3 checkout lines. So I want to make the store where everyone has to go through every single line. This makes it really hard to leave the store. And so big resistance is going to be series. You have to go through every single one individually. B wants us to make a circuit where there's the least resistance. And again, we have to connect the resistors in a way where they actually get voltage and current. So here I want least resistance, so I want options. I want to be able to go through this light bulb, or this light bulb, or this light bulb, right? So small resistance is where I can choose. I could go through 1 or 2 or 3. So that makes it a lot easier to get out of the store, right? Imagine the whole imaginary scenario where you walk into a Walmart and every single checkout line is open and you can go through any line 1 through 24. That would be amazing. You would have a really small resistance. It would be really easy to leave the store. So small resistance is going to be parallel. Easy to leave the store. So then C is asking which one has a bigger current. Well, we just talked about total resistance, and I should probably say resistance total. So a small total resistance, I'm trying to figure out, these have the same batteries, so these all have the same voltage total. So I'm trying to compare current. That means I'm probably using Ohm's law. Total voltage equals total current times total resistance. Well, these both have the same total voltage because they have the same battery. But if I want a big current, if I want to make this number big, I have to make this number small. Otherwise, when I multiply these together, it will no longer equal this. So if I make this number big, I have to make this number small to keep this equation correct. So if I want a big current, I want a small resistance. So small total resistance gives a big total current. And that means I want to, so bigger current, that's going to be B because that's parallel. Again, you're at the grocery store. If you have a lot of lines open and you can go through any of them, but you don't have to go through all of them, small resistance is easier to leave. More people are going to leave the store where they can go through any one of them, but they only have to go through one checkout line as opposed to having to go through every single checkout line. That's going to be a big resistance. Not a lot of people are going to be getting out of this store very easily. All right, and then this is really similar to like what we just did on our warm-up. Which circuit uses more power? So power equals current times voltage. We're talking about totals. Now, this is where it might be good to use one of our other power equations, because the thing that we know we have the same battery. So I know I have the same total voltage. We know they have different resistance totals, right? Depending on if we put this in series or parallel. So I really want this in terms of voltage and resistance, not current and voltage. So I could do, instead of current, well, I know voltage equals current times resistance, or current equals voltage divided by resistance. So I could put this in instead of current. So I could put total power equals, instead of current, I write voltage divided by resistance times total voltage. Voltage times voltage is voltage squared. Voltage squared divided by resistance. Now this is a lot nicer equation to look at. Because I know these have the same voltage, and all I'm trying to do is compare resistance, total, So if I want a lot of power, I want to divide by a small number, right? Divide by a small number means I get a bigger number. 1/2 is uh, bigger than 1/3. Or if you want, you can rearrange this. Total power times total resistance equals total voltage squared. This is constant, so I want to have a big power. I need to make a small resistance. So small resistance is going to be a bigger power, and that means parallel. Or B uses more power. Or develops more power is the phrase you hear a lot. And then just like our warm-up, which one of these is brighter? So brighter is pretty much talking about power. Brighter equals power. And that means that B is brighter because it has more power. And then which circuit does the battery die first? So the other thing we looked at, power equals the amount of energy used per time. So we have circuit B uses more power. And that means it uses up the energy first. So B uses more power, uses up the energy first, and that means the parallel circuit battery dies first. So yeah, advantages of parallel, smaller resistances, we get bigger currents, we can have more power for each individual device, the batteries will be brighter, but you don't just get that brightness out of nothing. If we have brighter light bulbs, more power used by each thing, that means we're using up more energy, and if it's connected to a battery, or things are going to die faster. All right, so that was really similar to the warm-up. I'm not going to spend a whole lot of time on that. And then 5 through 7, the last little bit is going to be us talking about one last little equation, our current equation. So 5 through 7 is relating this current to the amount of charge moving past the point. So that's using our equation for current is the amount of charge moving past a given point per time. So we have a light bulb has 5 coulombs of charge flowing through it every 30 seconds. So for A, current, we have 5 coulombs of charge passing through the circuit in 30 seconds. 5 divided by 30 should be 1/6, so what, 0.167? Yeah, 0.167. So the current through the circuit is 0.167 amps. Pretty straightforward. And then we have a 9-volt battery. So the light bulb, or not a 9-volt battery, this light bulb uses 9 volts. So the light bulb has a current of 0.16 amps, 1.167 amps, and it has a voltage of 9 volts. We're trying to find resistance. Voltage equals current times resistance. Resistance is voltage divided by current. So we use up 9 volts. 0.167 amps. I'm going to not round the previous one. So if we don't round, we get a resistance of exactly 54 ohms. All right, and then we have 6A, but no B or C. Yeah, I kind of messed up the formatting on that one, sorry. So 6, an electronic device has 800 milliamps of current flowing through it. So current equals 800 milliamps. So the first thing we need to do is convert this. We know there's 1,000 milli of anything in the actual thing. So 1,000 milliamps equals 1 amp. So if I want to convert this, my current is going to be 800 milliamps. I want to get rid of the milliamps unit, so I need to divide by 1,000 milliamps and multiply by 1 amp. That way my milliamp unit divides out, and we end up with the current 800 divided by 1,000 is 0.8 amps. So be careful of these. I definitely do have a lot of unit conversions on the upcoming test. All right, so we want to know, based on this, envision a meter. Yeah, I mean, it's not everyone has mathematical intuition. Like, that's the best, but that's fine. Some people are more artistic or better at languages. So sometimes it's nice to just write it out and do the math as opposed to trying to think too much about everything. So now we're trying to find the amount of charge that flows through per time. Well, I know current equals the amount of charge that flows past a point per time. So I'm trying to find charge. I can multiply time over. So charge equals current times time. So charge that flows through this in 1 second is just going to be that 0.8 amps times 1 second, which is going to be just 0.8 coulombs. So we have 0.8 coulombs flowing through this per second. Doesn't, yeah, well, getting bigger is nice because that's, you're saying going from, like, if I have kiloamps, so 1 kiloamp is just kilo is 1,000, so 1,000 amps. I find that easier. I don't know. I'm also just really used to unit conversions. Obviously, I've been doing this for more than half my life, so I mean, obviously it should be easier for me. All right, then I want to know how much of this is going through per hour. Charge flowing through per 1 hour. Well, 0.8 amps times time. But again, we need everything in base units, meters, kilograms, seconds, or other derived units like amps. So I have times 1 hour, but I can't leave this an hour. I need to put this, there's 60 minutes in 1 hour. I put hour in the denominator to cancel out. Then I have 60 seconds per minute. Minute divided by minute cancels out. So we end up with 0.8 times, that's a bit low. Should be 2,880 coulombs. 60 times 60 is 3,600. 2,880 coulombs. And this is per hour. Seconds, well, 60 times 60 is 3,600. Then we want to get the amount of charge that flows through per day. So still have 0.8 amps times 1 day. Well, I have 24 hours per day. Put day in the denominator to divide out. And then you could do 60 and 60. I'm just going to be a little bit lazy, and 3,600 seconds per hour. Put hour in the denominator to divide out. Or just 86,400 seconds in a day. And my calculator is freaking out at the moment. There we go. 69,120 coulombs per day. And then one last one, just another one of these. Superconducting wire can deliver 500 coulombs of charge in 2.5 seconds. What is the current through the wire? Current, just the amount of charge flowing past a point in a given time. So we have 500 coulombs in 2.5 seconds. 5 divided by 2.5 is 2. So we should just get a current of 200 amps, which is pretty high, but not crazy high for some industrial applications or like physics labs or things like that. That's the TI calculator. Yeah, I know a few people that worked at TI. I applied for a job there, but it was like super specific. Because yeah, that's the problem with getting a master's degree is like it's in a very specific subject. All right, so that's the rest of the classwork. Sorry the classwork took so long. I mean, try to work on it and finish it up. Honestly, this should just be kind of a completion grade. The goal of the classwork is it's really similar to the homework. Next week, we'll go on more complex circuits that are a combination of series and parallel. And then the week after that, you'll have a review and a test. And we're pretty close to the end of the year. There's not going to be a whole lot after that. But yeah, just make sure you're working on that, catching up. If you still haven't done one of the previous tests or quizzes, the Coulomb's law quiz or the waves test, please do that so I can give out keys and so people can actually check their work. If you're wanting to check what you got wrong on those, just go to tutorials and I can tell you what you missed on those so you can kind of figure that out. But yeah, other than that, just finish up the classwork, do the warm-up, finish up the homework. Most of these are nice, easy grades. And yeah, have a good day, have a good weekend, and I'll see y'all on Tuesday.